back. We got Adrian and Lisa got them. I don't know, it's like just the board pretty much. Y'all did them without the calculator? Like for example, you step on this one. You step through that. Okay, so we want logs, base 3, 127. Okay, remember yesterday we practiced rewriting these, like for example, log says 2, 8. We think in our head, 2, so what power would give us 8? Okay, for this one, you're thinking 3 to what power would give you 1/27. So we want, so the third power would be 27. If we did it on the bottom, it wouldn't be positive 3, it would be negative 3. Would give us a 27. Okay? So that's a good grade. All right, I'm making you about 20 more seconds. Then we're gonna get started. Already got some tickets out there. Good. Looking. See if a few other people got some stuff. Nice. Jesus has got it.
I got it.
Lovely. Lawrence has got it. Lovely. You can redeem these for stamps. We're practicing all around. But I want you still to get a chance to win. So get up. Okay. Here we go. Time to get started. For this first one, I already actually put it up here because I was kind of working with some people to recap from yesterday. If we're trying to find the log base 3 of 127, we know we need to raise it to the third power, but a negative third power to make that 27 on our denominator. Okay, so for the rest of them, I'm going to just take some volunteers around the crowd. And we got raffle day today. And today's prize is going to be some hot baked cookies. So, and you always luck out because you're the last class, so you just do the leftovers. So my other classes, there were 4 winners. Your class, we could have more. The benefits of 8th period. Look at all this. Right, Samantha. Oh, we're doing the second one, right? Second one.
-2.
-2. Call on the next person.
Sammy.
Someone who's not talking.
Come on, bro.
Let's do.
I was in the same
Oh my goodness. Take your time.
same elementary school. Oh, come on.
Gosh dang it, I'll do Carmen.
What?
She was quiet.
0. Hello. Because anything to the log, or like anything log of 1 is going to be a 0 power. Lovely. Next up, you get to pick Carmen. Diamond. What's next?
It's 2.
2. Next. Call on someone else.
Come on, Danny. We're in the same log band, bro.
Yeah, we're up in
Mom,
the
I'll pick mine because you're looking at me.
Who?
I was looking at you.
I got 3.
3. And last one.
Did you give my ticket?
Who else would you choose?
Mine, you have
4.
It's 4. All right, cool. I'm coming. Samantha, you come in. Okay, so with these,
I help you most of the time. Let me touch that.
with these, okay, with these, we're gonna take them, and today we've practiced yesterday evaluating, so actually finding the value. That's what you did in your do first. We're gonna take these. We're gonna use this first example of log base 3, and we're going to plot these points. We're going to graph it to see what the shape of our graph looks like. We actually got a preview of the shape of the graph yesterday because we talked about it being the inverse, and I had like a picture there to show you. But today we're going to look at the graph, and like we did on Monday with exponential graphs, we're going to draw what our logarithmic growth and decay graphs look like, and then we're going to do transformations. Okay, so from the top, I'm actually not going to use this grid because it's so small and I don't want to be confined by the little bitty squares. So if you want to use some other space, I'm just gonna draw an axis like this and just label the points that I want, okay? So the weird thing is that we're going all the way from 1/27, the little fraction, all the way up to 81. I'm probably actually not gonna plot that last one, 81. We should have a good idea what the graph looks like before that, okay? So let's think, if this is like 1, then 1/27 and 1/9 are both gonna be between 0 and 1, pretty close to 0, right? So if our first point is 1/27 -3, it's gonna be really close to 0, but then down 3, like right there, right? 1/27 is a little fraction that's close to 0, and then its output y value is -3. Hold on. So we plot it right there. Okay, 1/9 is slightly bigger, but still really close to 0. And that 1/9 goes with -2, so that would be like right here, still not at 1 yet. So notice all of these points are really close to the y-axis. You're gonna notice that's gonna be our asymptote here in a second. Okay, the next point is 1, 0, so that's right here on the x-axis. Then we've got the point 9, 2, so now we get to go all the way out to 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're gonna go up to 2. And then the next one's gonna be way out at 27, so I'm not gonna go all the way out there, but picture it, way out here at 27 would be up at 3. So in general, we're growing, we're getting bigger, but pretty slowly, right? As we go out from here on. Okay, so we're close to the y-axis, so if we go ahead and try to sketch our graph, we're approaching the y-axis, and then we are going through 1, 0, and it, oh gosh, steady, let's go. Thank you, slowly grow. I don't know why that's so hard for me. Slowly growing, like that. My picture looks really bad, but you'll see in a second a pretty picture. Okay? So in general, a logarithmic growth graph has a vertical asymptote right here on your which axis? X or Y? Y-axis, and then heads up, slowly growing like that. Yep.
Will we be like having to find the domain and range?
Yeah, so in a second we're going to do very similar to earlier this week with the growth graphs, where we're going to draw our like main graph and then list the characteristics of the domain and stuff so that we can always refer to them. Okay, cool. So in general we know it looks like this for log base 3, and then we're going to notice that it's similar for log with any base that's bigger than 1. We actually, like I said, saw this yesterday. Remember we talked that the log is the inverse of an exponential graph? So we talked about how this point 1, 0 had to be there because if you switch your x and y, if we switch 1, 0, what do we have? 0, 1, and that's the point we had coming from our growth graph, and notice all of these points are switched, so this is the inverse of that exponential growth graph we did earlier this week. Okay? Cool? Ooh, very nice. Okay, so let's go ahead and record this in our notes, and then like Jason said, we're gonna go into the domain, range, all those things. These graphs, I mentioned this yesterday, are not on your problem set for this week that's due on Monday. So you will have some graph questions on next week's problem set at the beginning of the problem set, so you can get some practice with this, because it will be on the quiz on Wednesday. So to study for the quiz, you can start your problem set next Monday, and then also we probably might not get through all the practice problems today, so you can always finish off any of those to help you practice, and I can check them if you want. Cristobal?
So the quiz is gonna have this week's lesson and
Yeah,
then
anyone remember yesterday when I said that everything up to the quiz stops on what day? Monday.
Okay.
Everything through Monday. The only thing won't be there on there is Tuesday because it's the day before the quiz.
Okay.
Okay? Cool. Alright, logarithmic functions and their graphs. Let's take a look and draw our growth graph and our decay graph, and I've got them up here on my yellow poster I'm going to be referring to, but you guys are going to have this in your notes, so you can split it down the middle if you'd like, because we're going to talk about growth, then we're going to talk about logarithmic decay. Okay? The one we saw in the do first was increasing, slowly at the end, but increasing. So that was an example of logarithmic growth. I didn't like this marker. I'm going to switch. Logarithmic growth. And you're going to have a curve that looks really similar to the one that you had in the do first. Anytime your function is f of x equals log base b of x, where b is bigger than 1. So for example, we had log base 3 and they do first, and 3 is bigger than 1, right? So that's why our graph looked the way that it did. It looked like a logarithmic growth graph. That means it could be log base 100 of x as well, right? Anything bigger than 1, and then our graph is going to go through where on the x-axis?
0.
0, 1. 1, 0, cool. And then it's gonna approach the y-axis, so there's a little asymptote if you want to put a dotted line on the y-axis so that you know that's an asymptote, and then it heads off to infinity over there. Slowly, but it's headed to infinity. There's not a horizontal asymptote up there. It's not leveling off, it's still heading up, but just slowly. Okay? So let's talk domain, range, all of the things. Domain and range. You could look just at the picture if you'd like. However, we could also think about the fact that this is the inverse of this graph, right? If it's the inverse, then x and y switched. So what's going to happen with our domain and range? They're going to switch as well. That's what I'm trying to say, that they're going to switch as well because domain is x, range is y. So if x and y switch, your domain and range will switch. So who remembers the range of the exponential graph, because that's going to be the domain of our logarithmic graph? Isaac?
The range was 0 to infinity.
Yeah, it started at 0 and went up to infinity. Now it makes sense because ours starts at 0 for our x's and goes to infinity. There's no negative x values, right? Okay, cool. Let's talk range. What was the domain for our previous graph, Maggie? And it makes sense because here for our range, we've got all the way from the negatives up to the positives, all real numbers, negative base or infinity. Yeah. Okay, next up, intercept. I've done this so many times today, like, I don't need to write down this graph anymore. Ready to be done. Okay, intercept. If it was for the previous exponential graph, 1, 0, 0, 1, we just said it would be 1, 0, and y'all can see that on your graph. And then for your asymptote, it used to be y equals 0, this horizontal line. Now it's vertical, so it's not y equals 0, it's x equals 0. So notice everything's just switching. It's all coming from that exponential graph, and it's the inverse. Okay, the limits our end behavior get a little funky. So let's chat about that. The first limit, when we describe the left side of our graph, usually we say x, bless you, is going to negative infinity, right?
Yeah.
However, we actually can't write this for the first time for our left-hand limit as negative infinity, because do we ever get to negative infinity? Do our x values ever go that far? No, there's like a wall at 0, right? The furthest we can go over is 0. So we're going to say as x gets closer and closer to 0, because that's the furthest left it could ever go. And the closest we can get, we're talking about from the right side, right? Like we did on the last unit, we put a little plus or minus to talk about whether we're on the right side or the left side. We can be on the right side of 0. We can't be on the left side of 0 because there's nothing over there, right? Okay. Just to the right of 0, we've got this piece of our graph. See how it's next to 0, but it's not quite there? Okay. Where is that part of the graph headed, Jose? It's headed down to negative infinity, right?
Yeah.
Okay. And then let's talk about the other side. The other side can go on forever and ever and ever because there's no asymptote. And as we go out, we're also going up. It's not a drastic up, but it's still going up, up, up. So we're going to say that that goes to infinity, positive infinity. Okay? All right, so that's the key information about our logarithmic growth graph. I'm going to get you started on the decay with the picture and the equation, and then y'all are going to write all this stuff for the decay graph. Jesus, question?
For the limit on the second part, why can't it be like 0, negative?
Gotcha. It's for this?
Yeah.
Okay, so we're talking about the left and right side of our entire graph. So usually we look way out at the ends as x goes to infinity and x goes to negative infinity. This one's still good. X goes to positive infinity. However, on this side, our graph, we never make it over there to x going to negative infinity. The furthest left we can get is x is going to 0
So we're looking at it from like,
from the right side.
yeah, from like this point of view, I guess you could
So we don't have a part of the graph that's
Yeah.
approaching 0 from the negative side. Yep.
Is that why you put the x to 0 plus? Because we're on the right.
Okay, next up, decay. And then I'm gonna release y'all to finish this one.
What's so funny?
Similar to our growth graph, for a logarithmic growth, this is gonna be logarithmic decay. So our equation is gonna be f of x equals, and it's gonna involve a log, but this time it's not gonna be log base b of x, it could be negative log base b of x. Remember, for exponential decay, it also dealt with when we had a negative, but we had a negative exponent, right? This time it's like a negative log. Or do y'all remember the other option? It could be a negative or what for exponential decay? Or a fraction. So here we're gonna say this. Or also watch out for equations that look like this. Either of those are gonna be graphs that are decaying. Okay, so let's think about what that looks like. If it's negative log base b of x, a negative out front of a graph is like, think about x squared. If I put a negative in front of x squared, what happens to it? It reflects, I saw Brandon go, it reflects across the x-axis like this, right? So this graph, we're just going to basically flip or reflect, and it's still going to be at 1, 0, but it's going to be approaching here and leveling off here. It's like we took our graph and flipped it. And our asymptote is still on the y-axis right there. Okay? So using that picture, go ahead, write all the important info about that graph, and while you're doing that, when Joanna comes back, I'm going to go ahead and bring tickets to people that I owe one to. You're doing wonderful, and who else? Jesus, you said something, or you asked me a question. Jose said something. What did you say? Okay, anyone else? Did I miss anyone? Okay, do you want to redeem? Oh no, you don't. You'll still get your tickets. Yes. You can post. Fridays are the best. You let me know. Okay. All right. You ready yet? Are we ready? Give me a few more seconds. I'm gonna erase this and put up the textbook version.
Nope.
Okay. Here's like the textbook pretty version of the graph that I sketched too, if you don't like my handwriting. Okay, so can I get one volunteer to give me the domain and range from the crowd? Adrian. 0 to infinity and the range, give me both. Negative infinity to positive infinity. I know this is small, but you can be listening to the person sharing the answer as well. So check your answers. Okay, next up our intercept, Jimmy.
Intercept would be 1, 0.
1, 0, same place right here. And then our asymptote, Luis. 0, it's in the same place, x equals 0 specifically. And then our limits, Isaiah.
As x approaches 0 from the right, f of x is infinity, and as x approaches infinity, f of x is negative infinity.
So that's the only one that changed, right?
Yep.
And this one, this limit, as we go to 0 from the right, is positive infinity, it's headed up. and as we go out to infinity, it's headed down slowly to negative infinity, okay? Okay, so we now have 4 graphs, right? 2 that look like this, 2 that looks like this, so whenever you get an equation, you need to be thinking, is this exponential or logarithmic, okay? And then is this growth or is this decay? So quick speed round, I'm gonna write down an equation. Okay, raise your hand, exponential, logarithmic, growth, or decay? Diamond? And exponential or logarithmic growth? Exponential growth, right? Because there's not a log in the equation. Okay, what about?
What is that?
1, that's 4, sorry.
Logarithmic.
Logarithmic what? Growth, cool. Okay, if I say,
Wait.
Oh, okay.
Wait, stop.
Face.
logarithmic what? Decay, because of the negative, and then logarithmic because it's still ln, but this is basically log base e to the x, but we just don't write it like that, we write it like this, right? Okay, and then last one,
My hand already.
First of all, his hand was already up.
Jason. Not logarithmic, look at it, is there a log?
Sorry. What was that word?
Yes.
Exponential.
Exponential decay, this one, right? Okay, so whenever you classify that as one of the 4, then you also need to be able to picture the graph. Like, right now we're using our notes and our posters, but like, we need to know which of the 4 graphs it looks like, because we're not going to be able to do a transformation of the graph if we don't know what the original graph looks like, right? So all 4 of these we've got now, and they're all pretty similar, and so it gets kind of confusing because you got like 1, 0 and 0, 1, and people are like, oh. So you got to make sure you're really systematically saying which graph is this, sketching the original graph, and then using that to shift, dilate, all the things we're going to be doing, okay? Okay, so let's shift over to transformations. Can I get someone to read right here where it says example? Let's figure out what we need to do first. Josh, go for it.
Ready?
Yep, I'm ready.
Use the graph f of x equals log x to decide the transformation that results in each function. Then sketch the graph of the function. Be sure to indicate any asymptotes or intercepts. Clearly label the end behavior of each graph.
Lovely. So first thing we got to do is describe the transformation. So in words, say, I want to translate it 3 units up, or like whatever we're doing, okay? The second thing we need to do is then sketch the picture, okay? Third thing, tell if there's any asymptotes, what they are. Fourth thing, identify the intercepts. And fifth thing, got a lot to do, we gotta find the end behavior with our limits. Cool? Okay, all that is what we're gonna do. So let's start on this first one kind of together. Can someone describe for me what type of transformation we would have if we're adding 4 inside of the equation? Justin? Left 4 units. So I'm going to use the word translate. It would translate 4 units to the left. Okay? Alright. Let's go ahead and sketch that. So again, I'm looking at my graph. This is log. So I'm thinking, definitely not exponential, definitely logarithmic. Okay. Is it logarithmic growth or decay? You just shout out. Growth. And so I'm picturing to start off with this graph, because I know my graphs really well because I'm studying, and it looks like that. That's the one we just drew. And now I want to pick that graph up. If I could, if it was like a string, I would literally pick it up and put it 4, like Justin said, to the left. But because we're drawing it, it means you got to take all the pieces and draw them 4 over. So the dotted line, the asymptote, if it's at 0 and we go 4 over, 1, 2, 3, 4, now it's going to be over here at -4. Our intercept is over here at 1, 0. I'm also going to move that over 4. 1, 2, 3, 4. It's gonna be right there, headed down, and then headed up to infinity. So it looks the exact same, just for back, okay? So what is, we got 1 done, we got 2 done. What is our new asymptote? Because they asked us to write that down, Hillary. X equals -4. Look at where my purple line is, it's at -4. What is my new intercept? Look at where my dot is on the x-axis, Jesus. -3, 0, good. -3, 0. And then take a second and try to write down your limits while I give out some tickets. Raise your hand if you're a ticket owed person. You too?
No,
Oh, no, that's just my hand.
I did the same thing that.
Stop doubting me. Where did the limits? The limits for this one.
I owe you.
Wait.
Write down those limits, try to write down your limits.
I don't like
Okay. So just check, oh, you got them, Joanna? Or questions? Need help? Okay, sorry.
So would it be like limit?
Okay, bring it back.
4?
The quicker y'all turn those voices off and bring it back, the more we're gonna be able to get there. Cool. Because, think about before, one of them was 0 from the right, one of them was infinity. Notice we no longer have that 0. We moved over, and so now this is as x approaches Cristobal what?
4.
4 from the right, because that's your new, or sorry, negative 4, right?
-4.
Will you still use the
Thank you.
Because we're still looking at the graph just to the right of -4, rather than to the left of -4. And then, where is that part of the graph headed, Jose? Negative infinity. And then on the other side, it's gonna be the same thing, because it's infinity, it's headed off to infinity, okay? Okay. I'm gonna check in with some people that maybe if any of that isn't clear to you, make sure to advocate for yourselves, let me know and I can help you out. What I want y'all to do is try this second one, and if you have extra time, you can go on to the third, but we're gonna talk about the third because it's got a multiplying times 3. On this one though, let me clarify something. I want you to find 1, the description, 2, the sketch, 3, the asymptote, but I actually don't need you to write your intercept because you're gonna notice it's going to move, the dot is gonna move off of the x-axis and be somewhere else, and so we can't really call it an intercept anymore. The intercept is gonna be some other random point, and I don't need you to find it for the purpose of today, okay? So for this one, doing everything except for the intercept, okay? Good. Go. Talk to your neighbors about where we go.
What?
This is wonderful. Okay, so this is, usually we say the left side of our graph is
Can we
asymptote,
move the asymptote
but
down?
in these cases, we actually don't go that far, and so we're going as far as
So
we
it
can,
stays
and
at
our
0.
wall is right here, our asymptote.
the intercept
So we're
would
saying
know the
it's
asymptote.
Asymptote
where's our
stays.
graph headed?
Asymptote stays.
On this one,
Yeah.
we wrote this one as x goes to 0. Did you get it? Instead of the negative infinity.
You still
No,
got
no, the way it ranks,
For this
what
one,
we
we
wrote
wrote
is,
right?
for this one, instead of.
We still gotta move the asymptote down, the intercept down,
Cute.
like, okay,
It was 1.
When you're moving off the right.
This is on the outside.
How you doing, Juan?
No.
So, good, so go down 5. So what's the asymptote? Because when you have -5 on the outside,
You didn't know what I was
same
asking?
thing as x squared.
Sorry, I don't speak Italian.
You know, x squared looks like,
You wanna
sorry,
talk?
behind you. Looks like this, and then if you say x squared -5, we talked about in unit 1, that's gonna take it down 5 and look like the same graph. Okay, if I add, or if I subtract 5 inside, that moves it forward 5, right, left or right, it's gonna move it. So this one was on the inside and moved it left, this one's on the outside, yeah. And then that's multiplying, so it's not gonna be, it's not the same as like a plus 3. Right, this is multiplying, we'll come back in a second, that's gonna be like stretching the one. Lovely, seeing pretty graphs, so pretty. Good, so this time, since you didn't move it side to side, did this asymptote right here move anywhere? When I move it down, it just like stays on that line. It doesn't mean
I think you do the same thing as the other one where you multiply like the intercept by 3 and then you add
right there. And then the graph actually is more.
Like there's a way to get. Wait, but that is just an answer to like 3, right?
I don't understand what I think.
Yeah, I know what you mean. Which way would it?
So I think we work our way from the inside out. So I feel like we would do the left part first and then we would do the 3 after.
Okay, so then we have to move it to.
And then 3, no, up and down.
But that's for the exponential.
That's what I'm saying. I'm guessing that's what we do.
Oh.
I don't know. That's what I said. I'm guessing. I'm confused.
Because this is still log graph. So every log graph is right here. Yep.
That's such a
Wait, y'all actually how about no? How about you split that?
And so notice with this one, because we didn't have that right dotted line,
Wait, y'all have to play
yeah, because it would be left.
Sure, well, my accounting pays
so how are you guys? How are you guys? Oh, on the key? No, I brought it. Oh, okay.
Okay, team, here we go. Log x minus 5. We're going to talk about the third one because I've had a couple people ask me about that mysterious 3. But as I walked around, I think everybody was done with this one, at least with the picture, if not with all the details. So let's talk about what happens when we have a log x minus 5. Where does it go? Where does it go, Joanna? Oh, no, the second one. She jumped to the third. 5 units down. Boop, right? Okay. So I'm not going to graph the original one because I think most of y'all have this, but really quickly just to check. 1, 2, 3, 4, 5. So your new graph should look something like that, right? Okay. So your asymptote, check it, is at 0 still. Your intercept, I told you we don't need to find because this point is down here at 1, -5 if you want to check your picture. But is that an intercept anymore? No. That's just a random point. You could find this intercept, see where it's crossing.
Yep.
And I drew it like that. Your drawing might look slightly different. You could find it by setting this equation equal to 0 and solving, but we haven't solved logarithmic equations yet, so we'll do that next week, okay? So that's why I said don't worry about the intercept for now. Limits headed to